So today we are going to see the topic counters in unit 3. In unit 3 we are going to see the topic counters. Now what is counter? So a counter will be having a group of flip-flops connected together to perform counting operations. So usually group of flip-flop will be calling it as register. Okay. So counter is a register or a group of flip-flop connected together to perform counting operations. It will count the input clock pulses. The counter will count the input clock pulses. That is number of clock pulses which is coming into the input. It will count. The number of flip-flop used and the way in which they are connected determine the number of states. So the number of states of the counter is determined by the number of flip-flop used and the way in which they are connected. Two broad categories. There are two broad categories of counters. One is asynchronous counter or ripple counter, and the second one is synchronous counter. So there are two broad categories. One is asynchronous counter, another one is synchronous counter. Another name of asynchronous counter is ripple counter. Asynchronous counter is also called as ripple counter. So in asynchronous counter, they don't have fixed time relationship with each other. In asynchronous counter, they are not having fixed time relationship with each other. Triggering does not occur at the same time. That is, we will not be providing the clock to all the flip-flop at the same time. So in asynchronous counter, we will not be providing the clocks at the same time. So they do not have a common clock pulse. This asynchronous counter or ripple counter is not having a common clock pulse. First, we are going to see a 2-bit. This is the diagram of 2-bit asynchronous 2-bit asynchronous. So first one is asynchronous 2-bit asynchronous binary counter. Binary counter means it will count from 0, 1, 2, 3, again 0, 0, then again it repeats. So this is binary count, 2-bit asynchronous binary counter. So the term asynchronous means you are not giving the clock to all the flip-flops at the same time. You are giving clock directly to the first flip-flop, and then for the second one you are taking the output, the complement output of the previous stage to the next stage. So you're not giving the clock, you are giving the clock directly to the first one, and for the second one and for the successive ones, you will be taking the inverted input of the previous stage and you are giving to the and giving us clock to the next stage. Okay, so this is the diagram. So then what your the type of flip flop you used for this counter is JK flip flop. So this is JK flip flop you have used. You have used two flip flops. So for 2 bits you are using two flip flops and you are made both J and K of both the flip flops high. So what are the things we have done? First one is you made you used two flip flops. First one. Second one, since it is asynchronous counter, you have given clock directly to the first one, and for the second one, you have taken the output, inverted input of the first one, and you have connected to the second one. So here, the you do not have a common clock, and the triggering will not occur at the same time. Okay, then you have made that uh, the J and K inputs of both of the flip flops high. Now we are going, this is the clock. So clock is nothing but the square wave. Now we are giving in, we are going for the working. So since we are giving clock directly to the first flip flop, for ever, this is a positive edge triggered flip flop. So there are the triggering is nothing but changing the state, making the flip flop to change its state is called triggering. So there are two types of triggering. One is edge triggering and next one is level triggering. There are two types of triggering. So please listen. This is a clock. So these are the two edges of clock. This is positive edge and this is negative edge. So there are two edges and this is level. So these are the two edges and this is level. So there are two types of triggering, that is edge triggering and level triggering. Edge triggering means making the flip-flop to change its states at this edges. This is positive edge and this is negative edge. If you are making the flip-flop to change its state at the positive edge, it is called positive edge triggered flip-flop. And if you are making the flip-flop to change its states at negative edge, then it is called negative edge triggered flip-flop. Now this is level. If you are making the flip-flop to change its state at this level, then it is called a level triggered flip-flop. So this flip-flop is a positive edge triggered. Our flip-flop is nothing but a positive edge triggered flip-flop. So this is the positive edge. So since you are connecting the clock directly to this first flip-flop, the first flip-flop will change during every positive edge. During every positive edge of the clock, this output of your first flip-flop will change. So we are going for the uh, working. The initially the output of both the flip-flops are 0. Okay. So output of both flip-flops. So we are going for the working. So initially both the flip-flops are 0. So if you are having 0 here, actually here you will be getting 1. So since we have put an inverter, that 1 will become 0 here. So this is a negative edge, positive edge triggered flip flop. This flip flop will change its state only if you are having 1 at this place. Once again, I am telling you know that both the inputs, both the outputs of the flip flops are complement of each other. So if you are having 0 here, you will be getting 1. But since you have introduced an inverter or a bubble, that 1 will get inverted and will be getting 0. So whenever you are having 0 here, it will not conduct this second flip flop. When you are having an output of 0 here in the Q naught, this flip flop 1, this is flip flop 0 and flip flop 1. The flip flop will not conduct. So only if you are having 1 at the Q naught, then here you'll be getting 0. That 0 will be inverted to 1. Then this flip flop 1 will conduct. Okay. Now I am going for the working. Initially both the outputs are 0. So you are applying at that time. Here you are having 0, that's 1, that 1 has inverted to 0, so it will not work. This second flip flop, that is ff1, will not work. So initially both the outputs are 0. Now you are applying clock, it will become 1. But at that time here you will be having 0, so this flip flop will not work. So same output you'll be getting here. You are applying the next positive edge. During the next positive edge, this 1 will become 0 here. But at the time here, if you are having 1 here also, you are having 1. This flip flop work and this 0 will change to 1. Why? Because when in a JK flip flop, if both J and K are 1, the output will complement. Okay. Now your output is 0 1. Now again you are applying clock. This 1 will become, the 0 will become 1. At that time the output what you are having here, that is in this place you will be having 0. So this flip flop will not work. So you'll be the same output you will be getting at this place. Okay. So you'll be getting 1 1. Next, during next clock pulse, this 1 will become 0. So at that time you'll be having 1 here. So this flip flop also work. So this will again change to 1. So you are getting 0 0 0 1 1 0 1 1. Again it is repeating. The sequence is repeating. Again I will explain once more. So this second flip-flop will conduct only when you are having an output of 0 here. Okay, make the first point. Now, initially both the inputs are 0. And this first flip-flop F naught will change the state during every positive clock edge. This is the first positive clock edge. This is the second. This is the third, and this is the fourth. During the first positive clock edge, this will change to 1. But at that time, this flip-flop will not work. Why? Because here we'll be having 0. Since it is positive clock edge, the for 0 input it will not work. So we'll be getting the same output. Now during the second clock pulse, this 1 will change to 0. At that time, what we're having is 1. So this flip flop will work. So this 0 will change to 1. So this is a JK flip flop, and both the inputs are made high. So for every clock pulse, it will toggle. Next, during the third clock pulse, this 0 will change to 1. But at that time, the value what we're having is here is 0. So the same output will be coming in the flip flop 1. Again, you are during the fourth clock pulse. During the fourth clock pulse, this 1 will change to 0. At that time, the value what you are having is 1 here. So this 1 will also change to 0. So again, the sequence is repeating 0 0 1 0 0 1 1 1 0 0. This is the working of asynchronous 2-bit ripple counter. So the same diagram. Here you are applying the main clock pulse only to the f of naught. So already I have explained. You are giving the main clock pulse only to the f of naught. The clock for the next flip flop is taken from the previous complemented output. So from here you are giving the clock. So all inputs J and K are made high. So this is a timing diagram. So this is your clock. First positive edge, second positive edge, third positive edge, and fourth positive edge. So this is Q naught bar. This is Q naught bar. So initially we are assuming Q naught and Q1 as 0. We are assuming Q naught and Q naught and Q1 as 0. Okay. Now please listen. During the first clock edge, this is Q naught. It will change its state during every clock pulse because you are directly connected to the clock. So during this is the first clock pulse. It is changing from 0 to 1. So during the next positive edge, it is changing to 0. It is again changing to positive, again changing to negative. So this is Q naught will change its state during every positive edge. So now you come to Q1. So first, after drawing this Q naught, you draw Q naught bar. So Q naught bar is nothing but the just reverse of Q naught. So if you are having 0 here, you are having 1. So if you are having 1 here, 0, then you draw Q naught bar. Now your Q1 will conduct only if we are having Q naught bar is. So first you have to draw the clock. So how to draw the timing diagram? So first you have to draw the clock. Then you have to mark the positive edges. This is the positive edge. This is the positive edge. This is the positive edge, and this is the positive edge. Now you forget about this Q naught bar. Hmm? So you leave some space, then we can draw this Q naught bar. So without Q naught bar also we can write the outputs Q naught and Q1. So first you you check the output Q naught. So the Q naught is nothing but the output of the first flip-flop F naught. So we are giving the clock directly to this flip-flop F0. So it will change its state during every positive edge of the clock pulse. So this is a positive edge triggered flip-flop. So it will changes the states during every positive edge of the clock pulse. So this is the first positive edge. And initially we are assuming that both the inputs are 0. So Q naught is 0. So since J and K are 1, during the first positive edge, it is the 0 is changing to 1. And during next positive edge, this 1 will change to 0 because J and K are 1. So output will toggle. During the next positive edge, again it is changing to 1. The next positive edge, it is changing to 0. Okay. Now, this is the output of Q naught. Now, you come to the flip-flop 1. The flip-flop 1 or the second flip-flop will conduct only when you are having Q naught is equal to 1 here. So whenever you are having Q naught is equal to 1, then only the second flip-flop will conduct. So now you check this Q naught. So here it is, here the value is 0. Then only it is changing to 1. So here this value is actually 0 to 1, you have to consider as 0. So here you are having 1. Similarly, here it is changing to 0 to 1. So it is 0 only. So this is 1. So the value of Q naught is 1 at this place and this place. So once again I am telling, so the second flip-flop will change the state only when you are having Q naught is equal to 1. So Q naught is equal to 1 means at a positive edge, you have to consider only the positive edge. You have to consider only the positive edge of the flip-flop. These are the positive edges. And the first positive edge, its value is 0. The second positive edge, its value is 1. Third positive edge, its value is 0. Fourth positive edge, its value is 1. So the second flip-flop will conduct only when you are having Q naught is equal to 1. These are the values for Q naught is equal to 1. So initially it is, we have taken it as 0. So in the first clock pulse positive of its value is 0, so it is not conducting. Then it is coming to the second positive edge, its value is 1, so it is conducting. Similarly, the third positive edge, its value is 0, so it is not so it is not conducting, so the previous value will be maintained. Now at the fourth clock edge, its value is 1. So this 1 is changing to 0. So once again I am telling, these are the positive edges. These are the positive edges, and our second flip-flop will conduct only during when you are having Q is equal to 1. So at this first positive edge, it is 0. This is 0. At the second positive edge, it is 1. At third, it is 0. 4, it is 1. So we are considering the value of Q naught as 0. Then during the first positive edge, its value is 0. So it is not changing. The same value is coming. So during the second positive edge, the value here is 1. So the second flip flop will change its state. So the 0 is converted to 1. Again, uh, coming to the third positive edge. At the third positive edge, the value is 0. So the second flip flop will not conduct, and the same output will be maintained up to next clock, next positive edge of the clock. At the next positive edge, the value here is 1. So it will toggle its output. So this is the output waveform of your timing waveform of your 2-bit binary This is a binary state sequence 0 0 0 1 1 0 1 1 again 0 0. This sequence you will be getting. So this is the sequence what you will be getting 0 0 then 0 1 1 0 1 1 0 0. This is LSB, Q0 is the LSB and Q1 is the MSB. Okay. So here we are writing the table. Clock pulse, initially we are considering both are 0. Then you are applying the first clock pulse, you are getting 0 1. You are applying the second clock pulse, you are getting 1 0. You are applying the third clock pulse, you are getting 1 1. And you are having after the fourth clock pulse, you are getting 0 0. And the cycle will repeat. Next is 3-bit binary counter. And we are considering the outputs as 0 0 0. And in this 3-bit binary counter, so similar to the 2-bit counter, only if you are having 0 at Q 0, this flip-flop 1 will conduct. And another thing, the flip-flop 2 will conduct only if flip-flop 1 is conducting. If flip-flop 1 is not conducting, then the flip-flop 2 will also not conduct, and the output remains the same during the previous stage. Okay, now we are starting the initial state we are considering as 0 0 0. Here also to the flip-flop 0 or the first flip-flop we are providing the clock directly. So during each positive edge its output will change. So during the first positive edge, here you will be having 0 will be converting to 1. At that time, here you will be having 0, so this will not conduct. So this is, if this flip-flop is not conducting, this will also not conduct. So during the next clock pulse positive edge, this 1 will conduct to 0. At that time, the value what you're having is 1 here. So this 1 will conduct to 2, or 1 will toggle to, sorry, this 0 will toggle to 1. And at that time, the value what you're having is 0 here. So this will not conduct. So the same output will be coming. So during the next clock pulse, this 0 will change to 1. This it will change to 1. At that time, you are having 0 here. So this flip-flop will not conduct. So you'll be getting 1. So if this flip-flop is not conducting, this all will not conduct. So during the next clock pulse, this 1 will change to 0. At that time, what you're having is 1 here. So this 1 will change to 0. At that time, what you're having is 1 here. So this 0 will conduct to 1. Okay. So next outputs I am writing here. Up to 1 0 0 I am written here. During the next clock pulse, this 0 will change to 1. At that time, you are having 0 here. So this flip-flop will not conduct. So you're here what will be having this 0. Since this flip-flop is not changing, this flip-flop will not also change. So you'll be getting 1 0 1. So during the next clock pulse, this flip-flop will change to 0. At that time, you are having 1 here. So this will conduct, and this 0 will change to 1. At that time, you are having 0. So this flip-flop will not conduct. So the same 1 will be coming as the output. During the next clock pulse, the 0 will change to 1. At that time, you are having 0 here. So this flip-flop will not conduct. So the same output 1 will be coming. Since this flip-flop is not conducting, this will also not conduct. So the same output 1 will be coming. So we'll check the sequence. First one is 0 0 0, then 0 0 1, then 0 1 0, then 0 1 1, then 1 0 0, then 1 0 1, then 1 1 0, then 1 1 1. 0 to 7 sequence, it is clearly coming. So this is the operation. You have to remember say a few things. This flip-flop 0 will conduct during every positive edge, or it will toggle its output every positive edge. And similarly, this second flip-flop will be conducting only if you are having 1 at the Q naught. And another thing, the flip flop 2 will conduct only if the flip flop 1 is conducting. Flip flop 1 is not conducting, 2 will not also will not conduct. Okay. So this is the operation. Now we are going for the timing diagram. It is very simple. First, your Q naught, the first flip flop will change during the every positive edge. So every positive edge it will be changing. Initially we are taking a 0, then it is changing to 1, then it is changing to 0, then it is changing to 1, then it is 0, 1, 0, 1, 0, 1, it is going. Now next we have to go for Q1. Q1 will conduct only when your value of Q naught is 1. So during the first positive edge its value is 0. During the second positive edge its value is 1. So I will put 1 here, 1. So here 0, here 1, here 0, here 1, here 0, here 1. So it will change its state during the positive 1 value of Q naught. So at this place it is changing to 1. Then during the next um, at this place you are having Q naught is 1. So again it is changing to 0. Then it is changing to 1 at this place. Okay. Now we are going for to draw the diagram of Q2. Q2 will change the state only when Q1 is 1. So here 0, here 1, here 0, here 1. So Q2 will change state only when Q1 is 1. At this place it is 1. Initially we have taken it 0. At this place it is changing to 1. Again here it is having 1. It is changing to 0. So this is the way for drawing your timing diagram for asynchronous 3-bit binary counter. Now we'll go for this is a sequence. So 0, 0 to 7. Then again it will repeat. Next we are going to see 4-bit asynchronous binary counter with a negative edge triggered flip flop. Till now we have studied positive edge triggered. Now we are going to see the negative edge triggered. We are going to see negative edge triggered flip flop. So negative edge triggering means here putting a bubble. So if it is positive edge triggered, there will be no bubble. So it indicates that this is a negative edge triggered flip flop. So negative edge triggered flip flop will change its states during the negative edge or trailing edge of the flip flop. So now these are the negative edges. So these are the negative edges. So similar to the previous counters, that is 3-bit counter and 2-bit counter, the first flip flop F0 will change the state during every negative edge. So during every negative edge it will change the state. Now the flip flop 1 will change the state when your Q0 is having a value of whenever Q0 is having a value of 1. So here it is having a value of 1, here it is having a value of 1. So here it is having a value of Q0 is having a value of 1 at these places. So at these places your flip flop Q1 will changes the state. Similarly FF2, FF2, the flip flop 3 will change the state only when Q1 is having the value of 1. So here it is having the value of 1. Similarly, the f of 3, it will change the state only when your Q2 is having a value of 1. So it is having 1 at these places. So this is the how to draw the timing diagram. This is a negative edge triggered flip flop. So it will change the state only during the negative edges. Okay. So this is so initially you take output of all flip floppers 0. So during the first negative edge, this 0 will change to 1. So this is this flip flop will this flip flop 1 will change the state only if you're having Q naught is equal to 1. So initially at that time it is 0, so it will not change. So if this flip flop is not conducting, this will also not conduct. So if this is not conducting, this also will not conduct. So during the second negative edge, this 1 will change to 0. At that time you are having 1 here, so this output of this flip flop will change. It will change to 1. At the time this flip flop having an output of input of 0, so it will not change. So if this is not changing, this output will not change. Similarly, during the next negative edge, the 0 will change to 1. At that time, the input to this flip flop is 0, so this output will not change. If this is not changing, this also will not change. This also will not change. Similarly, the sequence will go. Okay, this is the working of 4-bit negative edge triggered flip flop. Now you understand what is in my negative edge and positive edge. In the previous one, here you are not having bubble, so that is positive edge. If you are having bubble, it is negative edge. This is 4-bit asynchronous binary counter. Asynchronous binary counter means you will be providing clock only to the first flip flop. For the successive flip flop, you will be taking the outputs of the previous flip flop and will be giving the output. Okay, now we are going for asynchronous down counter. So there are two types of counter. So first classification is asynchronous counter and synchronous counter, and the next classification is down counter and up counter. So next classification is an up counter and down counter. So up counter will count the sequence 0, 1, 2, 3, 4, 5, 6, 7. In this order, if it counts, it is up counter. Down counter means if 0 means previous state of 0 is 7. So if it is 1 means previous state of 1 is 0. If it is 2 means previous state of 2 is 1. If 3 means previous state of 3 is 2. If 4 means previous state 3. So if a counter count in this sequence, then it is called down counter. So initially there are two types of counters, that is synchronous and asynchronous, that we can divide it into two. That is, one is up counter and another one is down counter. Down counter count from large to 0 and it will repeat. So it will count from large to 0, then it will repeat. Okay, so this is one example of up counter and down counter. Now, if you are having, you take this as present state and this as next state. Now, if present state is 0 in up counter, next state is 1. If present state is 1 in the up counter, next state is 2. If present state is 2 in up counter, next state is 3. If present state is 3 in up counter, it is 4. If present state is 4 in up counter, it is 5. If present state is 5 in up counter, it is 6. If present state is 6 in up counter, it is 7. If present state is 7 up counter, it is 0. Similarly, if present state is 0 in down counter, it is next state is 7. If present state is 1 in a down counter, next state is 0. If present state is 2 in a down counter, next state is 1. Similarly, for 4 it is 3. For 6 it is 5. For 7 it is 6. So this is asynchronous down counter. Okay. Now we'll see asynchronous down counter. So this is a asynchronous down counter. Here there is no bubble, so whenever you are having 0 here, it will, this flip flop will conduct. Okay, so in the case of up counter, you will be having a bubble, so whenever you are having 1, this flip flop will be conduct. But here in the case of down counter, whenever you are having 0, this flip flop 1 will conduct. Okay, now we'll go for the working. So first one, 0 0 0. We are giving the first clock pulse. You know that we are giving clock directly to flip flop 0. So for every clock pulse, this will change. So for the first clock pulse, it is 1. So during the first clock pulse, this 0 is changed to 1. At that time, you are having 1. So this flip flop will work. So this 1 0 will also change to 1. So at that time, this flip flop will also having an input of 1 here. So this also will change. During the next clock pulse, here you are having 0. So since you are having 1 here, this flip flop will not work. So you are having the same output here. So if this flip flop is not working, this flip flop also will not so work, will not work. So this output will be coming here. So during the next clock pulse, this 0 will change to 1. So since you are having 0 here, this output of this flip flop will change. It will change to 0. But at that time, input to this clock is 1. So it will not change. The same output is coming. Then during the next clock pulse, this 0 will be 1 will be changing to 0. Since you are having 1 here, this output will not change. So since this output is not changing, this will not also change. Next, during next clock pulse, this 0 will change to 1. Since you are having 0 here, the output of this flip flop will change. So at that time, the input to this flip flop is 0. So this will also change to 0. Then during the next clock pulse, this 1 will change to 0. So at that time, the input to this flip flop is 1. So it will not change. So if this is not changing, this will also not change. So in the next clock pulse, the 0 will change to 1. Since you are having 0 here, this also will change. So at that time, input to this one is 1, so it will not change. So during next clock pulse, this will change. And during that time, the input to the second one is 1, so it will not change. If it is not changing, this will not also change. So this is counting in downward. So this is down counter. Okay, the timing diagram. So this is a timing diagram of your down counter. So here the your first flip flop FF naught will change the state during this is a positive edge trigger. During every positive edge it is changing its state. So next this Q1 will change the state whenever you are having Q0 is equal to 0. So in the case of up counter, it will change the state whenever your Q0 is 1. Here it is changing the states whenever your Q0 is 0. So that is 0 to 1 transition time, it will be changing. Similarly, your Q2 will be changing the state whenever your Q1 is having a transition from 0 to 1. So it is changing the state. So here you are getting 1 1 1, then 1 1 0, then 1 0 1, then 1 0 0, then 0 1 1, then 0 1 0, then 0 0 1, then 0 0 0. So it is counting downward. So this is a timing diagram. Okay. Now we can go for asynchronous decade counter. Decade counter means it will count from 0 to 9. Okay. So 10 possible states it will be having. The modulus of a counter is a number of unique states that a counter will sequence through. The modulus is nothing but the number of unique states that a particular counter is counting or it is sequencing through. The maximum possible number of states is 2 to the power n. From 0, if you are counting, then it is nothing but 2 to the power n minus 1. Okay, where n is a number of flip-flops. The counter can also be designed to have a number of states in their sequence less than 2 to the power n. So we can design the counter which can have the states less than 2 to the power n. This resulting sequence is called truncated sequence. So if a counter is counting less than the maximum number, then particular sequence, the name is something called truncated sequence. Okay. Now counter with the 10 states are called decade counter. That is from 0 to 9. So to obtain the truncated sequence, it is necessary to force the counter to recycle before going through all of its possible states. So before going into all of its possible states, what we are doing is we are forcing the counter to recycle. Okay. Next we are going to see synchronous counter. So in synchronous counter, the clock is, we are giving the clock simultaneously to all the flip flops. Here you check, you can see that we are giving the clock simultaneously to both the flip flops. Okay, so this is 2-bit synchronous binary counter, similar to the synchronous counter. Here we have made J and K high, and here the output only the first flip flop we have made J and K high to the first flip flop, and for the second flip flop we have connected the Q output. The output of the first flip flop is connected to both the J and K. Okay, both the J and K of the second flip flop. So initially we are assuming that the output of both the flip flops are 0. So since the for the first flip flop J and K are J and K are 1, for every clock pulse the output of the first flip flop will change. So during the first this is a positive edge triggered flip flop. So during the first positive edge the 0 will change to 1. So at that time here you are having 0, so this value will not change. Okay, during the next clock pulse this 1 will change to 0. At that time you are having 1 here, so the output of this flip flop change to 0 to 1. So next, during the next clock pulse the 0 will change to 1. At that time you are having 0 here, so the output of this flip flop will not change, so this 1 will come again. During the next clock pulse this 1 will change to 0. At that time the input to this clock pulse is 1, so this 1 will change to 0. So it is, the sequence is repeating 0 0 0 1 1 0 1 1 again 0 0. This is the operation of synchronous 2-bit synchronous counter. Now this is a timing diagram. So this is a positive edge, and this is a positive edge, and this is a positive edge, and this is a positive edge. So the Q naught will change the output during every positive edge. Okay, and this flip flop 1 will change the state when your Q naught is 1. Whenever you are having 1, your flip flop 1 will change the state. So we'll be getting 0 0 0 1. This is 0 0 here, 0 1, then 1 0, then 1 1, then again 0 0. It is 2-bit synchronous binary counter. He will be providing clock simultaneously to both the flip flops. So next is, this is a binary sequence, that is initially 0 0, then first clock pulse 0 1, second clock pulse 1 0, third clock pulse 1 1. Again it will, the fourth clock pulse again it will repeats. This is 3-bit synchronous counter. So you check the diagram. Here you are having 3 flip flops: flip flop 0, flip flop 1, and flip flop 2. For the first flip flop, we have connected J and K to 1, and we have provided clock simultaneously to all the flip flops. For flip flop 2, we have connected the output of flip flop 1, and for flip flop 3, that is F of 2. For F of 2, we have connected the output of both the flip flop 1 and flip flop 2 and to an AND gate. Then we have connected it to the flip flop, the third flip flop. This is the first flip flop. The name is F of naught. The second flip flop F of 1, and third flip flop F of 2. So we will check the operation. So in terms of circuit diagram, the thing is, for the first flip flop we made J and K high. For the second flip flop we have given the output of first two. Second, for the third we have taken the output of first and second. You give it to an AND gate. Then we are give to the input of the F of 2 flip flop. Okay. Now initially the output of the flip flop is 0 0 0 0. During first flip clock pulse, this 0 will change to 1. So at that time here you are having 0. So this flip flop will not change the state. So here it is 0. At that time here you are having 0. here also you are having 0. So the input to this flip flop is 0, so it will not conduct. During the second clock pulse, this 1 will change to 0. Okay, at that time the input to this flip flop is 1, so this 0 will change to 1. During the application of clock pulse, the input to this flip flop is, it is uh, this is the state. No, this state we are considering. So input is nothing but 1 is 1, 1 is 0. So here we will be getting 0. The output will not change. So for the next one, this 0 will change to 1. At that time the input is 0. So this 1 will not uh, change. So the input to this one is nothing but this one. One is 1 and another one is 0. So the output is 0. This will not change. Now next, this is the output you are having 1 1 0. During the next clock pulse, this 1 will change to 0. At that time you are having 1 here. So the output of this 1 will change to 0. But at that time the input to this AND gate is uh, 1 1. So output is 1. So the 0 will change to 1. So 4. Next, this 0 will change to 1. At that time here you are having 0. So this will not change. So at that time the input to this AND gate is 0 0. So it is 0. So this output will not change. So 1 5. So it will function like this. Okay. So this is a timing diagram. The Q0 will change its state during every positive edge, and Q1 will change only when Q0 is 1, and Q2 will change only when Q1 is 1. Okay, so we'll be getting the 3-bit synchronous binary counter. So this is a counting sequence for 3-bit binary counter, that is 0, 1, 2, 3, 4, 5, 6, 7, and again 0. The 4-bit synchronous binary counter and timing diagram. So this is a 4-bit synchronous binary counter. So here you are having 4 flip-flops. For the first one, we have given, for the second one, we have given the input from the first one. For the third one, we have taken the input from first and second. And for the last final one, we have taken the input from the AND gate, that is from the second stage, and we have taken the output from the f of 2 and we have given. Okay, this is nothing but the 4-bit binary counter. The operation is similar to the previous one. Initially we have to consider the Q0, Q1, Q2 and Q3 as 0. Then we have to apply clock pulse. During every clock pulse, this Q0 will be changing the state, and Q1 will be changing the state only when Q0 is 1. Similarly, Q2 will change the state only when Q1 is 1. Similarly, Q3 will change state only when this Q2 is 1. Okay, so this is 4-bit binary counter. This is negative edge triggered. So this counter is negative edge triggered. The previously what is seen is positive edge triggered. This is negative edge triggered. So it is changing the state during the negative edge. Okay, this is 4-bit synchronous binary counter. Next we are going for the design of synchronous counter. Okay, so the first step is, so this is the circuit of general circuit of the sequential circuit. Sequential circuit will be having input and memory. Okay, now we are going for the steps for the design of sequential circuit. First, we have to specify the counter sequence and we have to draw the state diagram. And then we have to derive the next state table from the state diagram. Then derive the transition table showing flip-flop inputs and record for each transition. And then transition table is always same for the given type of flip-flop. Then transpose. Then by using K-map, we have to find the input of each flip-flop. Then we have to group and find the expression, and finally we have to implement. Okay. So this is a step to the design of sequential circuit that already we have seen. Next we are going to see up down counter. So already we have studied what is up counter and what is down counter. So now we are going to study a counter which will perform both the operation, that is up operation and down operation. So up down counter is one that is capable of progressing in increasing order or decreasing order through a certain sequence. So it will be progressing, it can progress in increasing order or decreasing order through a certain sequence. Up down counter is also called as bidirectional counter. Up down operation is controlled by up slash down bar control signal. So the meaning of up slash down bar is if you are giving a 0, it will count downwards, and if you give 1, it will count upwards. When the control signal is high, the counter goes through up sequence, and when the control signal is low, the counter goes through down sequence. Now this is here we are going to design a 3-bit counter. 3-bit means we'll be having the numbers from 0 to 7. So I will tell what is a up sequence. If present state is 0, the next state is 1 in up counter. If present state is 1, the next state is 2. If present state is 2, the next state is 3. If present state is 3, your next state is 4. If present state is 4, next state is 5. If present state is 5, next state is 6. If present state is 6, next state is 7. If present state is 7, next state is 0. This is up sequence. Then we will see the down sequence. If present state is 0, the next state is 7. If present state is 7, next state is 6. If present state is 6, next state is 5. If present state is 5, next state is 4. If present state is 4, next state is 3. Present state is 3, next state is 2. If present state is 2, next state is 1. If present state is 1, next state is 0. Okay, this is down operation. Okay, so this is nothing but the down operation. Now we will see the truth table or transition table. So X is a control signal, and when X is equal to 0, it will perform down operation. What is a if 0 is a present state, what is a next state? 7. If 1 is a present state, what is the next state? 0. If 2 is a present state, next state is 1. If 3 is a present state, next state is 2. If 4 is a present state, next state is 3. Similarly, if 5 is a present state, next state is 6. If 6 is a present state, next state is 5. If 7 is a present state, next state is 6. So first you have to write from 0 to 7, then you put 0 in the place of X, then you have to write the next state. Similarly, then you have to start writing from 0 to 7, then you have to put 1 in the place of X. Now it is going for, when you are giving X is equal to control input is equal to 1, it is going for up operation. If 0 is the present state, next state is 1. If 1 is a present state, next state is 2. Similarly, you have to write if 7 is the next state, present state, next state is 0. So we have completed the truth table. Then here this number will count up to uh, 7. So n is equal to the power n is greater than or equal to 7. So you need 3 flip-flops to implement. Here we are taking the flip-flop as T flip-flop, TA, TB and TC. So then we are comparing the present state A and next state A1 in T flip-flop. For 0, 1 and 1, 0 we are having 1, and for 0, 0 and 1, 1 we are having 0. So we check the present state. Here it is 0, here it is 1. So in the place of TA it is 1. Similarly, the present state of B is 0, B1 is 1. So here you are having 1. Here also C is 0, C1 is 1. So here you are having TCS 1. Similarly, we are filling the entire table. Then we are drawing three K-map for TA, TB and TC. Here the input variables are X, A, B and C. So individually we are checking the column of TA, TB and TC. We are plotting. So this is excitation table. By using this only, we have filled that TA, TB and TC inputs of the flip-flop. Then we are taking TA and we are checking the column of that TA, and wherever we are having one, we are plotting, and then we are grouping and we are writing the expression. Similarly for TB. Similarly, TC. Okay, after that, we are going for implementation. This is the implementation of up-down counter. So this is a control input, up-down bar X. So that we are this is X bar, and we are giving. Okay. So here we are used to three T flip flops, and giving the inputs TA. We are having the expression for TA that we are giving from the expression we are implementing. Okay.